I wrote pause here. It says this. I'm giving you two situations, Logan. Both of these blocks have the same mass, 10 kilograms. Both of them are on the same surface, so the coefficient of friction, mu, the stickiness, is 0.12. But you'll notice, Logan, in the second block, well, Logan, what's the difference between the two diagrams? What do you notice in the second block?
There's a down arrow.
And that's going to mean a different normal force. So we're going to do this all. We're going to write a vertical force equation. We're going to find the force of friction. We're going to write a horizontal. We're going to find the acceleration. And I'm actually going to do this all simultaneously. So just kind of draw a line down the middle of your page like this. Okay, folks? Logan, what does A want me to do? Write a... You know what? This is a job for a free body diagram. And the way I figured that out is I also noticed that B said find the force of friction. C said write a horizontal. There's more than one force in here. This is not just F equals ma. Let's do a free body diagram. So this first diagram, Logan, the one on the left, what are the forces acting on it? Get the obvious one. Good. mg. In fact, I can even do it in my head. It's going to be 10 times 9.8. I think mg is 98, I think. Are we sinking to the ground like, are we flying like Superman? So there's a normal force pointing up, and in this case, it's the same size as mg. I doubt that's the case in the next diagram. What else? Well, there's this 20 newtons. This is what we typically just call the applied force, and what we mean by that is something's pulling with 20 newtons, Logan. I don't care what, I just know something is. Is there friction in this question? Sure, yes.
Yeah.
Now, how do I know? Several ways. What does part B want you to find?
The force of friction.
If there was no friction, that would be a silly question for Mr. Dueck to ask. But from the diagram, Mr. Dueck hinted that there was friction by putting in the diagram a coefficient of friction. If I wanted no friction, I would write mu equals 0, and that's my way of saying we're on perfect ice, we can ignore friction. So friction is going to be that way. You okay with that? Let's do the free body diagram, Logan, you and I, for the second one. What are the forces acting on the second block? Get the obvious one. I agree. And here's the key, folks. There is going to be a normal force because it is not sinking to the ground like quicksand. It's not flying like Superman. Looking at that picture, is the normal force going to be bigger, smaller, or the same size as mg? I'm going to tell you right now, it ain't going to be the same size because it's extra vertical forces. Mackenzie, why is it going to be bigger? In fact, if you wanted to, I could tell you it's going to be mg plus 15, I think. So let's exaggerate it, Logan, so that it stands out. My scale is garbage, and this is why I told you at the very beginning when I first introduced free body diagrams, I said roughly to scale. If they're the same size, make them the same size. If one is bigger, make sure you can tell it's bigger. Is that all right? Again, Logan, we have our applied force, yes? Yeah. And there would be friction this way. Okay. Thank you, my friend. Adam, A says write a vertical force equation. We're going to do both of these at the same time, just so we can see the difference and how they compare to each other. Vertical is in the vertical direction. What's the vertical force equation in A? What equals what? Are you sinking into the ground like quicksand? Are you flying like Superman? Now, I used to say to you, well, that means the forces are, I'm looking for a word that begins with letter B, balance. Now I'm going to say, we can say that everything down equals everything up, or everything up equals everything down. So what equation could you write if everything up equals everything down? Yep. What equation can you write here if everything up equals everything down? Yeah. What if that 15 was pointing up? Well, then you would have Fn plus 15 equals mg, and you would minus the 15 over, and oh yeah, normal force would be smaller. You okay with that? Good. Good. Franz, what does B want me to find? Friction is what times what? I think you were the one that I went with last. No, was it you? Who did I go with? Friction equals... Sorry? Oh, Kenley. Friction equals... I knew it was in this direction. I had my vector off just a tiny bit. Kenley, friction equals what times what? So for both of these, it's going to be mu times the normal force, and part B, mu times the normal force. And in both of these, Kenley, I would say, I don't know the normal force. Oh, but look. In the first one, I know another force exactly the same size as the normal force, and it comes out of the vertical force equation that Adam gave me. What can I replace the normal force with, Kenley? Yes. So I can say this. Now again, let me emphasize, you will never ever hear me say friction equals mu mg. It does not equal mu mg. It equals mu times the normal force. And in this case, because it's a fairly basic question, the normal force is the same as mg. Here, it would be mu, I don't know the normal force. Oh, what can I replace the normal force with on the right-hand one? Keep reading. Yeah. So we're going to have to go like this. Bracket mg plus 15. Mu. Both of those, though, are the same expression, mu times the normal force. It's just we have a different normal force. You okay with that? Well, let's plug and chug, Kenley. On the left, we'll have 0.12 times 10 times 9.8. I can do that in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8. 11.4? No, I'm off. Hang on. I can do this in my head. I know I can. Let's try that again, Mr. Dueck. It's going to be 9.8 plus 1.96. It's 11.97. It's 11.76. Wow, I forgot to carry a 1. Over on the right-hand side, Kenley, it's going to look like this. 0.12 bracket 10 times 9.8 plus 15. Do that one again. Okay. It's going to be 98 and 50. It's going to be 113. 113 times 0.12. It's going to be 11.3 plus 2.26. So it's going to be 13.56. Booyah! I'm back. Had me worried for a second there. And of course, all of you are trying these on your calculator, right? By the way, Kenley, which one's bigger? Which one has a bigger force of friction? The left one or the right one? Be obvious. And why? Because someone's pushing down. This goes right back to when Jackson was trying to push the bench and you decided to sit on it. Of course, friction goes up. Okay. Riley, what's C want me to write? Good stretch. You're awake now? You're back? So horizontal, Riley, is in this direction. Look up. It's in this direction, right? Look at your free body diagram on the left. Who's winning? I think applied. I'm not sure, but I think so. Yes? Who's losing? Yeah. Now, here's what would be a bad thing to say. F applied minus mg. Those are not in the same direction. They can't go in the same equation. Force is a vector. Direction matters. And so we have to do stuff that's on the same level with itself. Okay? So what did you say, Riley? What's my equation? Winner? Minus loser? What does winner minus loser always equal? No. What does winner minus loser always equal? What? Help me out. Doesn't equal M. Come on, help me out. MA. Right? On the right-hand side, Riley, my friend. Who's winning? If I had to guess, who do you think is the winner? Who do you think is the loser? So winner minus loser, what does winner minus loser always equal? And you'll notice, Riley, it's the same equation for both, isn't it? Because it's the same thing going on. Horizontally, someone's pulling this to the right and friction is trying to slow it down. It's just that the actual friction force will vary. Cool. Franz, now I'm coming back to you. I've scrolled down. Franz, what's D asking me to find? How would I get the A by itself here? How would I get the A by itself here? Are you really, Mr. Dueck? You're saying the equation actually is going to be the same? So for both of these, I'm going to get this. F applied minus friction over M. I'm going to get A equals F applied minus friction over M. Talk me through this. I've scrolled down, Franz. How big was F applied? Franz, how big was F applied? I think it's from the diagram. Sorry? 20? Minus, and I calculated friction. It's 11.76 all over 10. Oh, I should be able to do this in my head. I'm dividing by 10. It's going to be 20 take away 11 is 9, take away 0.7 is 8.3, take away 8.24. 0.824? No? Oh. Someone shook their head. 0.824 for the first? Yes?
Oh, yeah, it is.
Shaking your head, trying to scare me. Nice try. I'm going to make a prediction because friction is bigger in D. I think our acceleration is going to be smaller. But let's crunch the numbers and find out. It's going to be 20 take away 13.56 divided by 10. 20 take away 13 is 7, take away 0.5 is 6.5, take away 6.44, 0.644? And it's the acceleration, so meters per second squared. Now, I want you to look at this equation right here. Don't circle it. I just want to talk about it, Franz. Here, I gave you friction and the applied force, and we found the acceleration. I would have no problem giving you the applied force and the acceleration and saying find friction. How would you get the friction by itself? What's right in front of the force of friction that I don't like? Swappy dance. In fact, once you had the force of friction, I would have no problem asking you to find mu, the coefficient of friction. And I think there's going to be one coming down the pipe where we do that. Just to turn the page. Because I'm introducing a new concept to you, friction, I'd like to just give you an idea, Antonio, of some values that are out there. These are different mu's, different stickinesses, different coefficients of friction. Wood on wood has a mu of about 0.25. You can reduce it with oil or grease, and all grease does is it lowers the coefficient of friction, and therefore lowers the force of friction. Steel on steel is about 0.5. If you lubricate it, steel on steel is about 0.1. Rubber on dry asphalt, this one varies a lot. It depends on your tires, anywhere from 0.4 to 0.7-ish, depending on how good your tires are, depending on how hot the asphalt is, because you have more traction on a summer day, because pavement when it gets hot is stickier, and rubber when it gets hot is stickier. Rubber on wet asphalt, you'll notice when it's raining, your mu goes down by about 50%. And what that means is it's probably going to take you twice as far to stop if you're having to do a panic stop where you're skidding and hitting the brakes. So slow down. Nothing to do with your driver's skill, Rowan. You can't argue with the physics. Okay. Rubber on ice is terrible. This is why driving on ice is so bad. Steel on ice is about 0.01. Hockey players would say, yeah, if you line your skates up just right, what's slowing you down the most is not friction, it's air resistance. So if you give yourself a push and just coast, the reason you're coming to a stop, it's more air resistance than friction. And speed skaters know this. That's why they have that tuck and they wear the fancy spandex and the helmets and all those technology to try and be more aerodynamic. All these values, Ben, are very approximate because there's different types of wood that has different stickiness. Depends on which tree we're talking about, what type of tree we're talking about. So there's a big variation, but just to give you an idea. Okay. Can we have a coefficient of friction greater than 1? Yes. Glue sort of does, but glue technically isn't friction. There's an electrochemical bond usually going on with glue, but often dragster tires have are greater than 1. Rubber on glass has a mu of about 0.2 approximately. If you ever try sliding rubber on a glass window, you'll notice, holy smokes, it doesn't want to slide very well. Okay. A dragster tire has a coefficient of friction of 2.8. These are good tires. Shouldn't a tire with so much friction slow the dragster down? Using principles of physics, explain why a high coefficient of friction is essential for racing. And then I have a hint. Antonio, what's the hint? Okay. Well, let's draw a Freebody diagram on the dragster. What are the forces acting on this dragster? Get the obvious one. Gravity. Is the dragster sinking into the ground like quicksand? Is it flying like Superman? No. I think there's a normal force the same size as mg. What else? Well, let's assume, Kenley, that the dragster is accelerating forwards. So there must be an unbalanced force that way. What force is that? What? And this is, Carlos, very counterintuitive. Friction in a car that's trying to accelerate points forwards. Riley, I'm coming back to you. Looking at this equation in the horizontal direction, who's winning? Who's losing? It's a trick question. Who's losing? It's a trick question. So no one. And that'll happen. Sometimes there won't be a loser. It's like kindergarten. Hey, everything's winning. Okay. And you'll get this. Here's your equation. Winner minus no loser equals MA. In fact, Jackson, if you wanted to take it further, you would say mu times the normal force equals MA. And then you would say, I don't know the normal force. Oh, but look. I know the force is the same size as the normal force, which is friction is not the same size as the normal force. What's got to be the same size as the normal force? What was that? If you want the expression for the acceleration of any car, it's mu mg divided by m. Oh, wait a minute. Actually, the m's cancel. The acceleration of a car depends on how sticky the tires are and what planet you're on. You don't accelerate as well on the moon, because g is less. So, as mu gets bigger, as this number here gets bigger, your acceleration gets bigger, and so this doesn't slow the dragster down, it speeds it up. Is that okay for an argument? Okay. And again, a lot of people that don't have a physics background, that wouldn't make sense to them. They would say, what, really? No, that would make it harder to drive. No, it makes it better to drive. Good stretch? Next page. I like example 7. I like example 7. I like example 7. What's part A asking me to find in example 7? Force of friction. What's part B asking me to find in example 7? Mu. I might feel comfortable on a test, Courtney, just giving you part B and expecting you to realize you probably need to find friction in order to find the coefficient of friction. What two words should I underline in this question? Let's do that right now. A force of 120 newtons is needed to push a box along a level road at a steady speed. If the force of gravity on the box is 250 newtons, what's the force of friction between the box and the road? What's the coefficient of friction between the box and the road? Any suggestions on how I might want to start this out? How do I know to do a free body diagram? It's mentioned the force of friction and it's mentioned the force of gravity. Is there more than one force in this question mentioned? I better do a free body diagram to figure this out. I'll do it right here. Ben, what are the forces acting on this box? Get the obvious one. And this one's a bit strange, Ben. I'm going to label it mg, but I can even tell you how big it is. They told me it's 250 newtons, not kilograms, newtons. So they did the mg for me. What else? Normal force going to be bigger, smaller, or the same size as mg. Do you see any other vertical forces hinted at or mentioned in this question? No. So you know what? It's the same. What else? Well, I guess we have an applied force. And Ben, I can even tell you exactly how big the applied force is. How big? How big exactly is the applied force? That's how hard we're pushing? Or pulling, but pushing? Is that okay? What else? Is there friction in this question? How do you know? Because what does part A ask me to find? The force of... Okay, so friction pointing to the left, bigger, smaller, or the same size as F applied? That's the question. Jack, what'd you say? Smaller? Ben, what two words did we underline? Bigger, smaller, or the same size? Why must it be the same size? Because A is, which means the forces are. Well, Newton, have I mentioned that Newton's first is a very powerful law. You can really, if you wrap your brain around it, figure out a lot of stuff. So Ben, I'm going to eyeball it. You eyeball it as well. Try and draw it the same length and try and draw it straighter than mine. Sorry, but I ran off the computer bezel and my hand suddenly dropped. Okay. Ben, what does A want me to find? Can anybody give me an equation in the horizontal direction? Jabber, loud and proud, what? Friction equals the applied force. I can go past going winner minus loser equals MA because, Courtney, since A is 0, it's a tie. Is that okay? So Jabber is saying, hey, Mr. Dueck, F applied equals friction. So friction equals, and here's the nice thing, Ben, they told me how big F applied was. How big was F applied? So how big is the force of friction? Done. Done. Cool. Savannah, what does B want me to find? Can you read to me the word that starts with letter C? The coefficient of kinetic friction. You know what it wants me to find? Hey, what's mu? I don't know. What's mu with you? It wants me to find mu. Savannah, what did I find in part A? The force of friction? I wonder if I might use my answer from part A to find part B. Let's find out. Kenley, what's the equation for friction? Friction equals what times what? Did you say mu? Ah, I just got a nerdy smile. Savannah, what am I trying to find in this equation? Which is which symbol here? Mu is right. You are right. How would I get the mu by itself? What's the Fn doing to the mu? So if I hear you, you're telling me mu equals friction divided by the normal force. Now, I know friction, 120. I don't know the normal force. Oh, but look. I know another force the same size as the normal force from my Freebody diagram, Savannah. What force must be the same size as my normal force from my Freebody diagram? Because we're not sinking in the ground like quicksand, and we're not flying in the air like Superman. And how big is mg exactly as a number? They told me. So just in our notes, Savannah, I'm going to write friction over mg. But if you in your homework went straight to saying, hey, it's 120 divided by 250, I'd be okay with that. What's mu? I don't know. What's mu with you? I think I'd do that in my head. 12 divided by 25. How do I divide by 25? Times by 4 and divide by 10. 0.48? Units. Someone said none. Someone said newtons. What did you say? And notice, by the way, this would be newtons and this would be newtons. What's newtons divided by newtons? None. They cancel. No units. Oh, you said no units?
Yeah.
I thought you said newtons. Sorry. Okay. How sticky is that? You know what? I could make a prediction. I could even go back to here and I could say this box might be rubber on pavement, or it could be steel on steel. I mean, maybe there's more to it than that, but that's good. That's good physics as well, Rowan. We look at balance another time, but that's good physics too. Turn the page. 2 more. Okay. I like example 8, I like example 8, I like example 8. Example 8 is a nice question. The other thing that's nice about example 8 is, aside from relativity, this is almost the whole year in one question. It says this: a dragster's tires accelerate it from rest to a speed of 32 meters per second in a distance of 64 meters. A says what's the acceleration of the car, B says what's the net force on the car, C says what's the force of friction between the tires and the road, and D says what's the coefficient of friction. I'm taking the question that we did last and I'm just expanding it. Now we're not going at a constant speed and I'm making you do some thinking. Okay. Sam, what does A want me to find? I don't think I'm going to go winner minus loser because I see a VI, I see a VF, and I see a D. I think I can go A equals question mark, VI equals 0, VF equals 32, and D equals 64. Do you see how I put that together? Now, if I hadn't seen all of that, then I would have said this is probably a job for a Freebody diagram, and I would have tried to go winner minus loser equals MA. How would I get the A by itself divided by M? But I don't think I need to hear, Sam, which equation am I going to use that has an A, a VI, a VF, and a D in it? There is one. Yeah, could you get the A by itself for me? I'll give you a hint. A equals... And yeah, you don't have to have these memorized. You might, but no need. They're on your sheet on purpose. So Sam, you went and looked at your sheet? Yeah? It comes from this one. VF squared equals VI squared plus 2AD. What's going to drop down like a domino? There is no VF in that equation. Thank you. Then? Thank you. Don't forget the squared. And then divided by? Good. Okay. This might work out evenly. You're going to get 32 squared minus 0 squared divided by 2 times 64. What do you get? Oh, you get 8? Even? Yeah. I need to change these numbers. That's a bad acceleration for a dragster because that's not even a 1G. Normally dragsters pull about 2. I must have wanted this to work out nice for you guys so you had nice numbers. I'll never do that again. Blake, what's B want me to find? The what force? Say it again. The what force? Say it again. Net force, you say? If I just see net force, that's code. Mr. Dueck is saying you can go straight to F equals MA. No need for winner minus loser. No need for free body diagram. Did they give me a mass, Blake? Yeah. Did they give me an acceleration? What did Sam just find for us? The oh. It's going to be 540 times 8. Oh, for Pete's sakes, do that one in your head. 500 times 8 is going to be 4,000. 40 times 8 is going to be 100. 5,160? No? Am I wrong? Am I way off? 4,320. Why did I get a 5 out of there? Dueck. Wow. And that's a force newtons. Is that right? Okay. Cool. Evan, what's C want me to find? Well, my first thought would be Kenley. Friction is. I would write this down and then I would say, I don't know the normal force. I better do a free body diagram. I think the normal force is mg as I'm imagining. I'm going to do a free body diagram. Do you have room over here? Most of you probably do if you've been following kind of my alignment. Somewhere, let's do a free body diagram. What are the forces acting on this dragster? Get the obvious one. Evan, my friend, get the obvious one.
Oh, gravity.
Yep. What else? Normal force. What else? Which way? Thank you. Oh, it drives me crazy when, because remember we did the dragster and the dragster tires a few questions ago where I said, what's the, and I still see kids, well, Mr. Dueck, friction's, no, it's not. It's this way. Okay, good. Friction is what times what? I don't know the normal force. Oh, but look. So I can use mg. Problem. Why can't I use Kenley's equation? I don't know, mu. Rats. This is still a job for a free body diagram. Look at your free body diagram. See it? Who's winning? So by the way, if you want to, you can put a little X through there. We can't use that because I don't know mu. Who's winning? Oh, someone's winning. Huh? Good. Friction. Who's losing? It's a trick question. What does winner minus loser always equal? What does it always equal? Say it again. And do you know what MA equals? Do you know how big friction is? It's 4,320, and I'm done. I didn't use mu. I didn't know mu, so I had to do something else. Free body diagram. That's almost so easy that it's tough, because that was actually easier than going mu times the normal force. But a lot of students, let's think outside the box a little bit here. Okay. Saving the best for last, Julie. What's D want me to find? What did I find in part C? Force of friction? I'll bet you they're related. Kenley, what's friction equal to? Mu times the normal force. What am I trying to find? How would I get the coefficient of friction by itself? Mu is going to be friction divided by the normal force. Yes? And friction, Kenley, you're right, is 4,320. I don't know the normal force. Oh, but look. Another force the same size as the normal force. Which one? Do you see how we hopscotched our way there? Now that I've hopscotched our way there, Courtney, I would have no problem giving you this question, but not asking you A or B or C, only asking you D and expecting you to realize, yeah, I can get all the way there in these steps. Okay? It's going to be 4,320 divided by, I've scrolled down, what was the mass? 540? Times 9.8. 0.816? Not very good dragster tires. Good tires for a car, though. Julie, what are the units for the coefficient of friction? Are none. Because it's newtons divided by newtons. The newtons would cancel. No units. Okay. So, Antonio, we can handle some pretty challenging questions if we don't panic. Good free body diagram. And recognize that if we can't find something in one method, maybe we can find a different method. Last one. I like example 9. I like example 9. Example 9 is a nice question. Kenzie, what does example 9 want me to find? Any suggestions on how I might want to start out? Oh, am I going to use VF and VI and D? I don't see nothing there. Do you see forces in the picture? More than one force? You know what this is a good job for? Except, did they give me a picture? I'm going to label the diagram rather than do a proper free body diagram. I think it's going to be clearer. So what are the forces acting on this, Kenzie? Get the obvious one. What else? Did you hear? Oh, speak to me, my nerdy girl. I love it. What did you just say? It's going to be smaller than mg because 25 newtons is already being taken care of by somebody off the screen. What else? Well, we have this one that we've typically called the applied off the page, force. Is there friction? Is friction 0.36? No, that's not friction. That's how sticky the floor is. I can use that to figure out how big friction's going to be, though. Okay. Whew. Let's write a horizontal equation. Who's winning? That's a vertical force equation. Okay, let's write that. Normal force plus 25 equals mg. Tuck that off in the corner somewhere. Let's write a horizontal force equation, because vertically it's a tie. Horizontal. Who's winning? Keep going. What does this question want me to find? Okay. Let's see if we can cut a little bit of corners and I can give you more time to work on the homework. Rowan, you with me?
Yeah.
Good, shut up. Here we go. You were whispering. Kenzie, what's the applied force? How big exactly? And then it's going to be minus, hey, what's mu? I don't know, what's mu with you? 0.36. And then from this equation here, can you tell me what the normal force has to be? mg plus 25, which you could do and calculate, but I'm a nerd. I'm going to try and do this in one step because I'm naturally lazy. All over 5.8. Is that a fraction? Is there more than one thing on the top? Not only am I going to put brackets around the top, I'm going to have brackets here as well. So it's going to look, if I wanted to do this in one step, and I can tell you're getting a little squirrely, so I will. It's going to be 45 minus 0.36 bracket 5.8 times 9.8 plus 25. Close off that bracket. Close off the top. Divided by 5.8. Do you get 2.678896552? No? No? Am I wrong? Maybe I made a mistake. 45 minus mu 5.8 times... Oh, Mr. Dueck. It's not plus 25, Mr. Dueck. Oh, I did make a mistake. Silly Mr. Dueck. Do you get 5.782344828? 5.78? Meters per second squared. Courtney, if I've done my job right today, I hope you didn't learn anything new. Like, I hope all I was doing was showing you how we can use free body diagrams and winner minus loser and just clarifying some questions that you might have had. Can I do this? Oh, I can do this. I'm hoping I didn't dramatically shock you or give you anything new today. What's your homework? I already said that you were capable of doing 1 and 2 and 3 and 4. So you can try number 5. You can try number 6. Try number 7. You can try number 8, 9, and 10. And you got 23 minutes to work on the homework, which is pretty good.